Have you ever considered how a complex machine learning model, like one that recognizes faces or translates languages, actually gains its understanding of the world? It processes vast amounts of data, learns patterns, and then makes incredibly accurate predictions. This remarkable ability to learn and adapt hinges on a couple of core components, which are adjusted during training. Weights and biases are absolutely essential for learning in neural networks because they are the fundamental parameters that the network adjusts to map any given input to its corresponding output. Think of them as the adjustable knobs and levers that allow the model to reshape data and find meaningful relationships. Without these adjustable elements, a neural network would be unable to learn anything at all, performing no better than a random guesser. So, why are they so crucial? Let us break it down. Weights representing the strength of the connections between neurons in different layers. When a signal passes from one neuron to the next, it is multiplied by a weight. A higher weight means that particular input connection has a stronger influence on the next neuron, while a lower weight signifies less influence. Biases, on the other hand, are independent values added to the weighted sum of inputs before an activation function is applied. They allow the activation function to be shifted left or right, effectively enabling the network to fit data more flexibly and determine the threshold for neuron activation. Together, weights and biases define the exact mathematical function that a neural network computes. The learning process itself involves iteratively adjusting these weights and biases. Initially, they are set to random values, and the network makes poor predictions. However, through a process called backpropagation, the network calculates the error in its predictions and then uses an optimization algorithm, commonly gradient descent, to figure out how much each weight and bias contributed to that error. It then slightly modifies these parameters in a direction that reduces the error. This cycle repeats hundreds or thousands of times, progressively refining the weights and biases until the network can make accurate predictions across a wide range of inputs. These learned weights and biases are what allow neural networks to perform sophisticated feature extraction and pattern recognition. For instance, in an image recognition task, specific configurations of weights and biases in the initial layers might learn to detect simple features like edges or corners. Deeper layers then combine these simple features into more complex ones, such as eyes or ears, and eventually into entire objects. The network literally builds a hierarchical understanding of the data by carefully tuning these millions or even billions of parameters. This intricate dance of numerical adjustments transforms raw data into actionable insights. Ultimately, weights and biases are the very fabric of a neural network's intelligence. They are not merely numbers, but the encoded knowledge and understanding that allow a machine to learn from experience, adapt to new information, and generalize its understanding to solve new problems. They embody the network's ability to recognize patterns, make decisions, and evolve its internal representations, forming the core adaptive intelligence of deep learning systems.